All right, so today we're going to talk more about derivatives. So last time we introduced the definition of the derivative. So just recap what we did last time. Well, first we talked about, well, the derivative comes from the idea of average rate of change. And so average rate of change is just this formula for slope, right? dy over dx. So average rate of change between 2 points is just the difference of y values and difference of x values at those points. So with limits, we have this idea of kind of jumping from 2 points to 1 point. So at every point, every moment between, like if you bring points closer to, if you bring 2 points closer together, you'll still be calculating a slope, average rate of change of those 2 points. But as you bring them closer and closer together, your average rate of change is getting closer and closer to essentially 1 point. So with limits, we're able to jump that gap and say that, well, instead of average rate of change, we can think of instantaneous rate of change, or like change at a point or slope at a point. This thing doesn't really make sense, in terms of what we think of change, right? Change has to be relative between 2 points in time, but with limits, we can kind of talk about this paradoxical thing called change at a point. So to talk about this change at a point, we think of instantaneous rate of change, or you could think of it as, in terms of graphs, the slope of a tangent line at a point. So we thought of this in 2 ways. This is our first definition using the average rate of change formula, which you see up here. The difference between the 2 y values of an arbitrary value f of x and the value that you care about, a, and then divided by the x values, x minus a. And then quite literally, you're bringing the x values closer to a. So at any 2 points in time, you're bringing the 2 values closer and closer together. And the other definition we had was using the difference quotient, which is really the same thing, but you're kind of viewing it in a different way. So the difference quotient, technically there's to make it look like the average rate of change formula, technically you would have in the denominator a plus h minus a, but the a's cancel and you get h. So h is the difference between the 2 values that you're calculating the average rate of change. A is the point that you care about, and a plus h is some point further down, or if h is negative, some point before. So as you bring that difference to 0, you're looking at the change happening closer and closer to a specific value. So taking limit, we can kind of jump between 2 points to 1 point. So this is how we define the derivative. The derivative of a function at a point is just literally that. It's the slope of the tangent line at that point, or the limit of the limit of the slopes of the secant line. So notice that this value here is the slope of the secant line. And then the limit is the derivative, or slope with the tangent line. So that's how we're thinking about derivatives. So we did some example problems last time. We'll do more today. And we'll also think of maybe think about the derivative as a function. So instead of like calculating the derivative at points, we can calculate like a general equation for the derivative, which sometimes you can do and sometimes you can't. So mainly we'll talk about functions where you can actually come up with an actual function of the derivative. But to start, I wanted to do an example that was that's in the homework for 2.1, which is this one here. And we'll just do it together. So we have our function is a piecewise function. It's x sine of 1 over x when x does not equal 0, and it's 0 when x is equal to 0. So notice this function up here doesn't exist at 0, right? But that's okay because you just tack in 0 when it's at 0. So first of all, I just wanted to kind of get the idea about what this thing looks like. So one thing, before derivatives, this could be a question about continuity. So can someone tell me either in the chat or you can talk as well, how would I determine if this thing is continuous at 0? What would I need to check?
You would need to check if you can find the same limit from both sides, left and right.
And specifically at what point?
At 0.
Yeah. So I'm looking at the limit of f of x. And what do I want it to equal? If this thing is continuous, what should it equal?
0.
Yeah, 0, which is our f of 0. So that's what it means to be continuous. So let's do that. Let's first of all, what is f of x as x approaches 0? So it's a piecewise function, so we had to think about left and rights and everything. So what does this thing look like? The left and right of 0. Yeah, it's a sine function. So let's look at the limit as x approaches 0 of x sine of 1 over x. So first of all, this is solving for continuity. How do we solve that limit? Can someone propose a method to solve this? So there is some theorem that we use when we see these. It could be a sine function, the weird angle. What should this tell you? Oh yeah, I could do that too. Let's do this in 2 ways. Oh wait, actually, sorry, we can't. So that is a method that we could do, but actually that won't work here. Are you thinking of using the sine of x over x property? So yeah, so let's think about that. Like, you want to turn this into this? Is that what you mean? Yeah, so can someone tell me why this is not, this is tempting to do because this looks like one of our formulas, right? Can someone tell me why this is not equal to 1? So by the way,
it's a fraction.
What's that?
Because it's a fraction.
So what specifically about the fraction makes this not work? Like, so look at like, what about the fraction makes it not work? So look at our formula here. So the denominator here is actually not 0, right? As x approaches 0, what is the denominator approach? So if I if I write it like this, as x approaches 0, what is the denominator doing? Yeah, it's going off to infinity, right? So this is not exactly the same as this formula, right? In this formula, okay, we have the limit approaches 0, but the angles don't approach 0, right? Angles are approaching infinity.
And the two infinities want to cancel out.
Yeah, we can't take the 1 over x outside of sine. So yeah, so as x goes to 0, do you agree that 1 over x approaches infinity? Does that make sense? Think about divide by small number, right? Number divided by something very small is close to infinity, right? Keep, change, flip. 1 over 1, or other way around, right? I would want 1 over infinity. That's really big, right? Anyway, is that okay?
Yeah.
Yeah, okay. So we can't really use that trick, but what's another trick that we have? What do you know about sine? Yeah, squeeze theorem is probably a good bet. So how do we start a squeeze theorem problem? So good, yeah. So this sine function, sine of 1 over x, is regardless of what the angle is. This could be what this thing inside could be whatever it wants to be, but by the squeeze theorem, or just by sine in general, this thing cannot go above 1 nor below -1. So what can you do next? So I don't care about sine of 1 over x, but I care about x sine of 1 over x. So let's just multiply everything by x. So now what does this tell you? Yes, that's correct. Sine and cosine as well. This is by unit circle. Yeah, so unit circle does not go beyond 1 and -1 for its x and y values. So if we take all these, if you take a limit to 0, right, this goes to 0 and this goes to 0. So that means, what is our only choice? The limit as x goes to 0. Zero. So yeah, notice if you incorrectly used this formula, you would get 1. But if you use the squeeze theorem, which is the correct way of approaching it, you get 0. So you tell me, is this continuous at 0? So go back to our original problem. Is this continuous? Yes, good. So it is continuous, but the question is, let's answer question 2. Is it differentiable at 0? So let me rewrite the problem and then let's think about using the derivative. All right, so how could we tell if this is differentiable at 0, right? We want to find, I'm going to say, does f prime of 0 exist? So Okay, what is f prime of 0? How do you find that? So we have a couple definitions, so it's further up there. So I'll write both of them out. So you tell me which one might be easier. I'll put 0.
Hey, Professor, sorry to interrupt.
Sure.
I was trying to sign in. I was having issues. Did you take attendance already?
Oh, don't worry about attendance for today. But
Okay, I'll be in class. That's fine.
okay.
Thank you.
Okay, so these are our two equivalent definitions of the derivative at 0. Which one do you want to use, you think? So you can say first or second. Yeah, let's use the first one. That seems like it could be nicer. So let's use the first one. The limit as x approaches 0. So what's f of x? What is f of x when x approaches 0? Well, we only have one choice, right? It's 0 only when x is equal to 0. But as it approaches 0, it's everything but 0. As it approaches 0, it's x sine of 1 over x. And then what's f of 0?
Zero.
Yep, so minus 0 and x minus 0. Okay, so what happens?
X and X cancel out.
Correct, yeah, so I just have sine of 1 over x left over. Now, can someone give me the reason why, or think about this limit and maybe say why, what it is? Think about what's going on in that limit. As x approaches 0, what is the angle doing as x approaches 0?
Is it going towards infinity?
Yeah, 1 over x is approaching infinity. So now think about sine itself, and what kind of function is it? Can you give me a reason why this should not exist? Let me rewrite it this way. This bottom one might be easier to say why. What do you know about sine? So bounded isn't really the issue, but think about when it hits its upper and lower bounds, right? So a limit means, so what does this mean? This is really a horizontal asymptote, right? So if this limit existed as the angle goes to infinity, that means that the sine values are approaching a number, right? So what do you know about sine that tells you that's definitely not true?
Professor, I'm sorry, I have a question.
Sure.
How come it's not 0 instead of DNE?
Yeah, so that's what we're trying to figure out, right? So, right. So, do you agree that these both this and this are the same kind of limit?
Right.
Yeah. So we're trying to figure out why it's DNE right now. So, yeah. What do you think about just the graph of sine even as sine goes off to infinity, or as the angle goes off to infinity? What do you know what sine is doing? Yeah, sine is continuous, but that really isn't a big deal. What type of function is sine? Sine, cosine, tangent, all those functions. what's true about them?
They're continuous.
They are continuous, but they're special, right? Those trig functions, they're really set apart from like a lot of other functions, right? What's different about trig functions that's not true about a lot of other functions we work with? How about this? Wavy, yeah. So what is the waviness?
Periodic.
Periodic, yeah. That's the big word. What does periodic mean is that what is sine? If sine looks like this picture forever, right? So what that means is that, well, how could sine be approaching anything as the angle goes off to infinity, right? Because what this is doing, what sine is doing, whenever you reach 2 pi, you just repeat this picture, right? So clearly that cannot approach anything, right? So this is D because it's periodic, right? Every 2 pi, it'll always have this wavy shape, right? It's not, right? This is not looking like this. It's not like waving down to 0, but it's looking the same forever, right? That's what periodic means. It's always going to look like this forever. So you put this off to infinity, and towards infinity, it will still look like that. Yes, that is true. That's something we can say in general. In general, if f of x has a period of p, has a period of p, so that what does that mean? Where it's equal and it's not constant, let's say. Then the limit as it goes to infinity, d, yeah. So all of those trigonometric functions, right, don't have any limits as x goes to infinity. Now, I mean, maybe if you tack on a 1 over x in there, maybe it can go off to 0, but periodic functions, they can't approach anything, right? Because it has to repeat itself forever. And repeating itself forever does not mean approaching anything. Yeah, so periodic functions are, their limits don't exist as it goes to infinity. Okay, so does that make sense? So if this is true, as the angle goes off to infinity, certainly sine cannot approach anything. So at the same token, since these limits are pretty much the same thing, as x goes to 0, sine of 1 over x can't approach anything. Because again, as x approaches 0, the angles are approaching infinity. Is that okay?
Can you explain what you were saying about as x approaches p?
Oh, p is just means, so this is the definition of periodic.
Oh, okay.
So there exists a number p such that if you add that number to x, it doesn't change. So for example, sine is 2 pi periodic. Since sine of, if you look at any value of x, and then you add the angle 2 pi, it looks the same, right? That's the same thing as like doing a 360, right? You're gonna the coterminal angle is still going to be the same. Tangent is also 2 pi periodic, but it's also, there's also a shorter period of pi. So tangent of x plus pi is equal to tangent. Those are 2 examples. The cosine is also.
So this applies to all trig functions.
Yeah. So by themselves. So I mean, like, for example, 1 over x is not periodic. Right? 1 over x sine of x, because, okay, maybe sine of x is periodic, but 1 over x isn't, right? So if you like multiply or add functions to trig functions, you may lose the kind of periodic nature. Is that okay for periodic? Okay.
Yeah,
So
understood.
cool. So returning to our question, right? We just found out that the derivative does not exist, right? When we calculated our derivative, we found that we ended up with a limit as x approaches 0 of sine of 1 over x. So now that doesn't exist. So, I mean, here's the answer to the homework. Last problem on 2.1. The derivative does not exist, which is interesting because it was continuous, right? So if you were to, you could graph this where you don't have to pick up your pen, but for some reason around 0, you can't graph it so nicely that the kind of slopes are continuous. So we'll talk more about that. So okay, one thing I did want to mention. Oh, yes. So for limits, yeah, infinity or negative infinity will still be does not exist. So, okay, so today we'll be talking about the derivatives as a function. So we'll be defining, so recall, so we had like f prime of a was equal to the limit, and we'll be using this definition more often now, as a plus h, and f of a over h. This was the derivative. So at a point. So what will be called what we'll call f prime of x is a function where when you plug in a value for x, you output the derivative at that point. So why? Sometimes you can do this, and sometimes you can't. Right, sometimes like in our piecewise function, right, the derivative didn't exist, right? It wasn't a it wasn't a function at x equals 0, right? If you plugged in 0, it wouldn't work. So, but for a lot of functions, a lot of the nice functions, we can do this. So, how we're going to find the derivatives, we'll just be doing just the difference quotient. So where x is now a variable, not an actual point. So you can also use the other definition if you like. So maybe like maybe y, what's another good letter? Let's say z. As z approaches x of f of, or yeah, f of x minus f of z over x minus z. That's also fine. So you can still use either definition, but for a lot of our functions, we'll be using this one more often. But at a point, sometimes the average rate of change definition is preferable. So let's do an example. So let's take the function f of x is equal to x squared. And what I want to do is find the derivative as a function. So in class last time, maybe we'll just do that example. We found like f prime of 2, I think it was, right? So what we did here was we did the limit as x approaches 2. Oh yeah, so if I did f of z minus f of x over z minus x, they're equal, right? That's fine. And to see why, all you're really doing is multiplying numerator and denominator by -1. So it's the same thing. So it's a nice thing about, slope and everything is that, oh, actually this, in this one, the order does matter, right? You have to do x plus h first and then minus f of x, right? If you flipped it, you'd have to negate h as well. So just be careful. Yeah, be careful about that. So what we did last time with the derivative of x squared, we did, was it f of x minus f of 2 over x minus 2. So was it x squared minus 4 over x minus 2, and then we calculated this, right? When we factored out the numerator and cancel, found that the derivative was 4. So what we're going to do now is, well, instead of looking specifically at 2, why don't we find a general equation for the derivative at any point? So that's going to be our goal here, is we're going to find the general equation for the derivative. So instead of like having to calculate like specifically a number at every single point, let's find a general equation for derivatives at all points. Okay, so let's do that. So the derivative is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. So notice this looks the same. Instead of plugging in actual value for x, we're just leaving it as x now. Okay, so what is f of x plus h? So that means you plug in x plus h into the function f of x. So for this problem, what does that look like? This is important to know how to express. Okay, yeah, so you foiled it out. So, right, you plug in the actual expression x plus h in the place for x. So yeah, so it looks like that, and then minus f of x is x squared. And yeah, so when you FOIL that out, distribute that, it's x squared plus 2xh plus h squared minus x squared all over, oops, all over h. Okay, so what happens? How can we simplify this?
Factor it out in h.
Well, first, if I get rid of the x's, now I can get rid of the denominator h. Yeah, so these h's, okay, so let's write that out. So after getting rid of the x, or it's the x squared. Yeah, now what can you do with the h's? So just a little hint, people kind of get confused of when can you cancel out terms. If you ever get confused about that, like when can you cancel out the h's, I like to recommend factor first. So when can you cancel out? Yeah, how do you factor out the numerator? It's a nice intermediary step if you get confused by how to cancel terms in numerator and denominator. Yeah, so if I factor out the numerator by h, then it's clear how you can cancel out terms, right? Now is it clear how the h's cancel? Yeah, so now you can cancel the h. And then what happens as h goes to 0? What are you left with? Right, so yeah, you're left with 2x plus h, but then as h goes to 0, I'm just left with 2x. So my original function was x squared. And I found out that the derivative was 2x. So this means that now I can calculate the derivative at any point I want. So what is the slope of the tangent line? Power rule, what's that? Slope of the tangent line at x equals 7. What would you tell me? Yeah, we haven't done power rule yet. Power rule comes from this, what we're doing now. Power rule is a formula that you come up with. It's not the derivative, so we'll do that today. We'll prove the power rule today. So you may have heard of something called power rule to calculate derivatives, very quickly. But again, those are formulas that come from this. So this is the meat and bones of what a derivative is. Later, we'll find ways to calculate limits a lot quicker. There's a general rule for doing derivatives, or for certain types of functions. You can find a general formula to find the derivative, but right now we don't know how to do that yet. And again, on the test, if I ask to find the derivative using the limit definition, I would want you to do this way, because it's very important to kind of understand where these things come from. Because again, if you lose the fact that the derivative is just a rate of change, right? Then power rule, there's nothing in power rule that tells you rate of change, right? That's just a formula. But using this in this definition, it is rate of change. So we'll talk more about that later. Okay, so sorry, my computer's a little laggy right now. Well, let's do another problem. Let's do f of x is equal to 1 over x. And let's find the general derivative. We don't have any formulas yet, right? We're bare bones right now. So, well, first of all, there's something I do know about the derivative. Like, let's say before I even calculate it, I might have an idea of what it might look like. Or based on what I know about 1 over x, I might know what its derivative could potentially be. So we know that the graph of 1 over x, if you don't know the graph, here it is. looks something like this. Sorry, I'm very laggy right now. So we have vertical and horizontal asymptotes at 0. So look at the tangent line at every single point. Try to imagine what the tangent line looks like. What is true about every single tangent line that you draw? Where's it pointing? Is this like in terms of like the sign of the number? Yeah, no matter what tangent line you draw here, the slope is always going to be negative. Sorry. Usually it's fine if I don't do camera. But every single tangent line you try to draw always have negative slope. So even one down here, if I drew it better, it's going to be negative, but might be closer to 0. So when we calculate the derivative, this should be a function that's always negative, and it's never positive. So we'll kind of come back to this and see if that makes sense. Okay, so let's do the derivative. Okay, so I have a derivative. I have a limit as h goes to 0. Now, how do I write? Can someone say how you write f of x plus h? So remember, this is 1 over x. Now, what does f of x plus h look like? And use parentheses to say it. So good, yeah. So h is in the denominator, so that's very important. So knowing how to plug in x plus h is pretty vital for this. Okay, so I have 1 over x plus h, and then minus f of x, which is 1 over x. And all over h. All right, someone tell me how you calculate this limit. What would your first step be? Like, how do you deal with complex fractions? Common denominator, yeah. Oh, yeah, common denominator. So what is the common denominator here? Yeah, I think I heard that. It was a little soft, but x times x plus h. Oh, not just x plus h, right? It's x times x plus h.
Yeah, that's what I think.
Yeah. So I actually have to multiply an x to this first term here, right? So using the common denominator, I have x divided by x times x plus h. And then to the second, I have to multiply an x plus h. Okay, so what happens in the numerator? What's left in the numerator when you subtract? Right, good, minus h. So we have x minus in parentheses. It's where you get a lot of problems if you forget parentheses. Right, if you don't have the parentheses, you might think it's positive h, right? But so the x's cancel. Sometimes I like to do, sometimes this divided by h can be very kind of annoying to look at. So one thing I like to do is just take out the 1 over h and then just write the rest of it. So I have minus h over x plus h. Okay. Everyone agree with that? Where we landed? Yeah. All right, so what happens? What can we cancel anything? Yes, I can cancel the h's. And now what is the limit? It's a little bit better. As h goes to 0, what happens? Yeah, negative 1 over x squared. So to power rule wizards, this makes sense to you, right? And we just proved it to ourselves. Can you tell me why this is always negative? So remember our supposition was that, oh, the derivative must always be negative because all the slopes that you draw have to be negative. Yeah, so, I mean, just by even the graph too, but just even look at this, right? X squared, this is always positive, right? And then negative 1 is always negative. So negative 1 over x squared. I guess looks like this. Oh, it's both, it's always negative, right? So notice you're always negative. Right, so you give me a value for x. So this is like 2 and this is f of 2 or f prime of 2. This is the slope of f of x at x equals 2. Okay. Let's do another one. Oh, any questions on that? The limit is the important thing. We'll talk about graphing later a bit more. Any questions on this problem?
Yeah, I have a question. Can you go over what you were saying about it being a negative, before you solved it?
Oh, so this is just kind of like, so before I even like approach this derivative, I might want to say, well, based on what I know about 1 over x, the derivative should look like something that's always below the x-axis. Should be always negative. Because all tangent lines are negative slope. So that was that. Yeah, I mean, you don't have to say this in the beginning. I was just kind of building up to something to do later. But do you see that? Like every single tangent line you draw will always have negative slopes. That should tell me that my derivative I should always be underneath the x-axis, right? These are all negative values.
Okay.
Why do the h's cancel? Right here, right? I have a 1 over h and then a negative h over x times x plus h. That's the cancellation here. Because this is all a product down here, right? H times x plus h, and then 1 times negative h. All right. Let's do another one. All right, so maybe you can tell me. Think about radical x. Where should the derivative be? Like, is it 0 anywhere? Is it negative anywhere? Is it positive anywhere? Where should it be? What do the tangent lines of radical x look like? Yeah, all tangent lines have positive slope. By the way, while we're here, what is 0 slope? Yeah, 0 slope is horizontal, right? So yeah, so things that are like that are constant functions are 0 slope functions. What is vertical? What's vertical slope? Yeah, infinity slope. So this could tell you that if you have a tangent line that's vertical, that the derivative doesn't exist there. There might be like an asymptote. So, by the way, okay. So let's think about radical x. So yeah, so do you see why all tangent lines have positive slope? So if I draw a tangent line here, it's positive. Here, it's positive. Here, it's positive. So in the derivative, whatever the graph looks like at the derivative, it should be above the x-axis. Should be it's greater than 0 and should be above the x-axis. Okay, so let's calculate. Limit as h goes to 0, and then you tell me what does f of x plus h look like? This is square root now. In other words, is the h inside the radical or outside the radical? Inside, yeah. You'll get something very different if you put it outside. How do you solve this?
Conjugate?
Conjugate, yeah. So let's do that.
It's interesting that because you end up with that on the bottom. That's there's no times.
That's 4h plus. Plus. Hey, can someone tell me what the numerator looks like?
X plus h minus x.
May speak a little louder. I think I heard someone talking. Yeah, I have x plus h, and then what's left? So remember, when you do conjugate, yeah, it's minus x. And now remember the big hint when you do these kind of conjugate-like tricks is don't need to distribute in the H, just leave it. All right, what happens to the X's? Cancel. Then what's left over? H's cancel, right? Didn't see that? All right, so as H approaches 0, what's happening? Am I allowed to just plug in H equals 0 here? Yeah, there's no problem doing that, right? So I have 1 over radical x plus radical x. Okay, so what's that? 2 radical x. So that's it. So let's do an example. The slope of the tangent line at, let's say, x equals 16. What would you tell me? I think we did this one last time, right? I think 16, yeah. That's 1 over 2 radical 16 over 2 times 4 is equal to 1 over 8. So cool, now we have a formula for the derivative of radical x. All right. Questions about that one? Okay. Let's do another one. All right, so first of all, let's look at the graph of sine. Then you tell me what the derivative what must be true about the derivative you think. So sine is a periodic function, right? It repeats every 2 pi. Well, the derivative can exist, right? You can draw tangent lines everywhere, right? That's fine. So the derivative just tells you the slope of the tangent lines, and that's okay to do, right? So yeah, remember, yes, yeah. So it's different from what we did before was kind of an infinite limit. This is a little bit different. So imagine the derivative, right? The derivative tells you the slope of tangent lines, right? If sine is periodic, can you tell me why the derivative must be periodic? Someone just kind of give a brief explanation why. Yeah, and exactly, because it repeats. So this tangent line here certainly has the same slope as this tangent line here, right? Yeah, exactly. These would be parallel, right? Every time we go 2 pi, you would get a parallel tangent. So just by knowing that, you can kind of guess what the derivative should look like, right? I mean, not precisely, but the idea is that like it should also be some sort of periodic function. Right now, I don't know if it's like maybe one that's nice, but at least it has to be some sort of repeating function. So let's.
I have a question.
Yeah, sure.
So wouldn't that tangent line hit the function twice?
Oh yeah. So remember last time when we say tangent line hitting once, you only really mean hitting once when you kind of zoom in. So when you zoom in at that point, the tangent line hits only once.
So it's fine if it intersects on the function again.
Yeah, that's fine over there. The idea is when you zoom in, if you zoom in enough, it will only hit once. That's the idea.
Okay.
All right, so okay, let's do it. So this is for sine. So the derivative. Oh, I gave away what the angle looks like, but hopefully we're okay with that now. All right, so I have sine of x plus h minus sine of x over h. All right. What do we do? So if you're here last class, we did kind of a similar question, but with cosine. Cannot factor out sine, right? These are different things, right? This is sine of x plus h. This is sine of x. Right, I have to use the angle formula. Right, so notice that sine of x plus h, something you really should remember, is sine of x, sine of h, plus, or sorry, not that, cosine of h, plus sine of h, cosine of x. So let's put that in. Sine of x, cosine of h, plus sine of h, cosine of x, minus sine of x. All of h. Okay, so what do you think so it might be hard to figure out how to solve this. Remember, the limit is h goes to 0, but do you have an idea of what maybe formula that we might want to use, or something about maybe trig functions? What should be ringing bells for you? And to give a hint, this is the bell that should be ringing. What bell does this ring to you? And maybe throw in the sign there. What do these three things scream to you?
Would it be undefined because the h is on the bottom? That would be 0.
Well, so if you plug in h equals 0, the numerator becomes 0 as well, right?
Do we use sine of theta over theta?
Yeah. So that's going to be the idea. Or theta is just a variable. It could be any letter you want it to be. So it could be h. So I see this sine of h, and I see this h here. So I probably want to use that. So why don't we let's isolate this part. So let's bring this over to the right side. So let's split it up. And now, so remember, these are all limits as h goes to 0. So remember, there's a limit here and there's a limit here. So what is this as h goes to 0?
Cosine x.
Good. So this goes to 1 as h goes to 0, and I'm left with cosine of x. So now I need to find this limit. So let me rewrite that bigger, and just note that we have this cosine out here. So now we're going to solve this limit. It's like a new problem now. All right, everyone okay at that step here? So we isolated the term with this sine of h over h, and left with cosine when we take the limit. And now we're looking at the leftover term. Yes, we can factor out a sine of x. Well, in fact, we can factor out of everything, right? Because sine of x has no h.
Could we do something with the cosine of h and the 8? Or
Can you say it louder?
could we do something with the cosine of h and the denominator?
Or like, can't do anything directly like this.
Yeah.
So I can only do it if it's sine of h over h, then I can, but not when it's cosine of h over h.
Why?
Well, let's just look at it. Yeah, there is a cosine of it. I'm just keeping it outside for now. What happens when you plug in h equals 0 for cosine?
Oh, okay.
So it's a lot different, right?
Yeah, okay. Thank you.
I didn't plug in anything yet. Sorry, I'm leaving out the cosine just so I can hone in on this limit. I haven't plugged anything in. I want to give myself more room.
Where did we get the -1?
I factored out the sine.
Ah, okay.
So yeah, there's a -1 left over. So are we okay getting to this point? So notice I can only factor out the sine because the limit is from h goes to 0 and there's no h here. So it's okay to factor that out. How do I solve that limit? So let's just kind of only look at this limit now. How do you do that?
Do we plug in 0 now?
So what happens when you plug in 0? You get,
0.
yeah, so I can't do anything there, right? So there has to be some trick, right, in order to solve this.
Is it like an identity?
Yeah, there's a trick identity. We might actually do this exact one earlier, a couple of weeks ago. Yeah, what trick identity do you think you want to use?
Wait, wouldn't that only work if it's cos squared?
Well, yeah, maybe you can multiply something to get it cos squared, right?
So you'd be multiplying cos.
Well, maybe not just cos, but maybe something else. Cos plus 1, yeah. If I multiply by cos plus 1,
Oh, conjugate. Okay.
yeah, it's kind of like conjugate, but for a trig. So what happens in the numerator? That's where you get a cos squared. Cos squared of h minus 1. So remember, the middle terms cancel. Yes, yes. So I'm multiplying just this fraction by cos h plus 1. So this is the result of doing that. Negative sine squared, yeah. Oh no, not the cosine. Just I'm leaving this outside.
Is the sin x also outside?
Yeah, that's out here, but being multiplied by this.
Okay.
All right, so yeah, we have negative sine squared. Okay. Remember, this is using this formula, right?
Wait, what happened to cosine squared? Did it cancel?
Sorry, we're using this formula.
So sine squared is negative.
Yeah, so like solve for sine squared, and then you can see how that comes about. Yeah, so I still have a cosine here. I'm just ignoring it for now.
So the sine h over h will cancel out, right?
Right, I'll give you a 1. Yeah, because it's just like this. That makes sense? Yeah. All right, so what is this limit now? Can you plug it in? What does that equal? What happens when you plug in h is equal to 0?
Wait, what about the plus cos?
That's out here. We already did that limit. That was from above, right? That was from here.
Right, so it doesn't get included in the limit.
Well, we already did it, right? Because I did I'm doing the limit of both. It's a sum, right?
Mhm.
I already did the limit of the second term when I split up the fraction. Now I'm looking at the limit of this first term, and that's all this work down here. We're left here. This is the last limit we need to do.
Okay.
Yeah. So what? Yeah, sine of 0 is 0, and then what happens to cos when you plug in 1 or when you plug in 0? Yes, it's 2.
1.
So this is just 0. That's the derivative. The derivative of sine is actually cosine. It's pretty surprising. It's
Can you
almost
go back up a little bit, please? On your thing?
how far up. Is that okay?
Yeah, thank you.
I find this kind of surprising. Just so sine and cosine are so nice that the derivative of sine is actually cosine. Just pretty surprising.
So what about the sine x that was multiplied to the limit?
Well, the limit was 0, so it's just times 0.
Oh, gotcha. Okay.
This kind of satisfies our kind of thought, right? That the derivative of sine should be periodic because sine is periodic. And it happens to be so nice that it's actually cosine.
Oh, on the division of 0, it's only dividing 0 over 2 over 0, not sine times 0 over 2 over 0. Is that correct?
This is just this equals 0.
Oh, okay.
Again, this is a sum over here, right? So, all right, so remember we have this fact here, right? That the limit of f of x plus g of x, I don't know, as x approaches a is limit as x approaches a of f of x plus limit as x approaches a of g of x, right? Yeah, so we did that one first. We found that was like cosine. And then the rest of it was just rest of problem. Yeah. All right. All right, so let's do another one. Slightly easier. All right, let's do x. So we did x squared before, right? Because that was 2x. So let's see what happens for higher powers. Let's do x cubed. So let's do it. The limit as h approaches 0. What does our x plus h look like here?
X plus h cubed.
X plus h cubed minus x to the third over h.
Does anybody know how to do that? X plus h cubed. You can just distribute forever, but anyone know like Pascal's triangle? Does that ring a bell to anybody?
Isn't that like x plus h times x squared? Something like that. I can't remember the whole thing.
Yeah. Well, if you draw a triangle, then you can figure it out. Like, so I'll do the first line. Has anyone seen this before for like binomial theorem? So like, what would the next line be? Like, what do you do?
1 3 3 1.
Can you tell me how do you get threes?
You add the two numbers above 1 plus 2.
Right, good. So what would the next line be?
4 6 4.
Right.
And then 1.
Good, yeah. So what is Pascal's triangle for? Very useful for. It's for doing powers of binomials. So yeah, so like the first line is, well, who cares what the first line? The rest is better. So like, so this line here, the coefficients, let's do just x plus, we don't have to put the h in there right now. Let's do like x plus y squared. So these are the coefficients of the term. So exactly what you have there is x plus y squared. So what you do is the first term is a 1, and the power is squared, and then y to the 0, which is 1. And then the next term is a 2. And what you do is subtract 1 to this power and add 1 to this power. So you have an x, subtract 1, and then you have a y plus 1. And the 2 comes from here. And then the last term is you again add 1, or so you minus 1, and you add 1. So the coefficients, it's x and y squared. So written out nicely, it's x squared plus 2xy plus y squared. And this is a 0. So can you tell me what the cube is? So now we're reading out the third line. So I have a 1. Where are my power? What's my power of x? What's my power of y?
X to the third, y to the 0.
X to the third, y to the 0, and then what's my next term?
X squared, y, y to the 1.
Right, good. And then what's my next term?
X to the 1, y to the square, y to the second,
And then what's my last term?
h to the third.
So let's do that here. So using that here, and yes, we could also just FOIL it out long ways, but there's a reason why I want to show Pascal's triangle now, because we're going to do this for all numbers, not just cubes. So I'm using this. I have x cubed h to the 0 plus 3x squared h plus 3x h squared plus h cubed, and then minus x cubed. This whole thing is x plus h cubed. Okay, so how do you solve?
Cancel out the x cubed.
Cancel out the x cubed, and then what's left over?
3x squared h plus 3x h squared plus h to the cube.
So how do you continue solving that?
Cancel the h.
Right. If you factor out an h in the numerator, now what happens? What happens as h goes to 0? (3x squared). So these go to 0. Okay, so that's 3x squared. All right, everyone see that? So what we're going to do is, instead of doing this for the 4th power, because it's going to be a lot of terms, right? Look at the 4th power. It's already 5 terms, right? Let's just see what the pattern is, and then we'll see maybe what happens in higher powers. So while I write out the triangle, let me know if you have any questions with what just happened. Maybe actually, can you tell me the next line?
5, 10, 10, 5, 1.
What's next?
6, 15, 20, 15, 1.
6 and 1.
Oh, yeah, 5, 6, 1.
Yeah. 7, so 21, 35, also 35, 7, 1, etc. So I'm going to label this as n equals 1, n equals 2, n equals 3. This will go on forever, right? But the idea is maybe you can find out like a good pattern, what's true about all of these. So if I had x plus h to the 7th, these would be my coefficients. It would be x to the 7th plus 7, x to the 6th, h, plus 21, x to the 5th, h squared, plus blah, 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 blah. The idea is that I don't want to do that. It's like pretend like we're too lazy to do all that, right? So let's just see about some things that are common about every single line. Someone tell me, like, is there a relationship between the n? Maybe not for the first one. Let's ignore the first one. What's a relationship between the n and the numbers?
N corresponds to the number of coefficients.
Well,
Oh, no, sorry. Nope.
almost.
They're like factors of that number. They can multiply into it.
Yeah, I think that's generally true. Yeah, n+1 terms. Maybe this more literally, like, where does n pop up? Like, how about this? Let's say we're at. Let's say we're at the kth row. What would my first term be? My first number? 1. What would be my second number? Right, whatever row I'm in. And notice,
Oh, they boy.
that second number is always, and second to last number is always the number of the row you're in, right? So maybe let's say this is the nth row. I would have 1 n dot 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 dot, and then what's my second to last? It's n and 1. And math can be funky. So give me the powers actually. So what would the power here be? What would I write here? So x to the what? Let's do for n now. Yeah, x to the n. And then what's my next term?
n+1.
Remember what I do? I minus 1, right? I subtract 1 to the x and I plus 1.
Oh,
So actually, well, first of all, this is my coefficient, right? So I minus 1, and then I add 1 to the h power. See that? So I may not know what the next term is, what the number is, but can you tell me the power? Like what would the x and h be? Yeah, so minus 1 at plus 1. So n minus 2, and then I get an h squared, right? But who knows what that number is? There is a formula for it, but it turns out that formula doesn't really matter because of the h. So all this happens, there's all these numbers and all these powers, but let's go at the end. So at the second to last term, I get an n, and then you tell me what the power would be, or the x and h powers. Yeah, there's a single power of x, and now h has the n minus 1. So notice how the second to last kind of just flip flop. And then what's the last term? H to the n. All right, so let's keep that in mind, that the most important terms, they are the ones that we can actually calculate. And even this last term is not really necessary either. Let's just keep this in mind. This is, all of this is x plus h to the n. All right, is that okay? We're just using the triangle right now. Again, there's a proof for the triangle, but you might see that more like in a discrete math class, using like something called induction. Okay, so let's figure it out. Let's figure out the derivative of any number, x to the any number. So h goes to 0, x plus h to the n minus x, yeah, minus, yeah, x to the n. Okay. So let's plug this in to that. So what I get, I have x to the n plus n x to the n minus 1h plus something x n minus 2h squared plus stuff. And then what are my last two terms? I have n x h n minus 1 plus h to the n, and then I have, so that's, I got, this is x plus h to the n, and I have minus x to the n, and this is all over h. All right, everyone see that? All I'm doing is just plugging in what we found out above for this here. Is that okay? If it's not clear, let me know.
I think it's a little confusing because you use like the letters and stuff. I think if it was like an actual problem, it'd be a little clearer.
Yeah, well, the idea is that we're trying to figure out something for a general number, right? Not for a specific thing. The idea is that, I mean, if you can accept this, do you accept this here? How this is equal to this? Just do it by the pattern, right? My first term is
She's on my phone. Yes.
x the number, and I have the number n,
Mm-hmm.
and then I subtract 1 to the power of x, n minus 1, and I add 1 to the power of h. So it's just, it's might look overwhelming, but the idea is that this will cancel out so nicely. Well, first, does something cancel out, first of all?
Sorry, can you say that again?
Oh, sorry, does something cancel out? Can you see a term that, yeah, that's x to the n in the beginning, and that cancel. So I have stuff. Okay, can anything cancel?
The age, I think.
Yeah. So notice why I put stuff here. It's because all the stuff has some power of h, right?
Mm-hmm.
When you factor out this h, notice the h goes away in the first term, right? But do you agree that every single other term will have a power of h? So this is, if this is overwhelming, just note that all terms here have powers of h greater than 1. So if I factor out an h, all this stuff, they all have h things. So when I cancel out, when I factor and cancel, I have this term here, n x to the minus 1, then plus stuff with h's. Yeah, of course. Well, when n is equal to 1, it's just slope, right? Well, even then, actually, it would be, it would just be 1. So what happens when h goes to 0? What do all these terms go to?
0.
Yeah, all these go to 0. So what's the derivative? It's n x the n minus 1. So if my function is x the n, my derivative is n x the n minus 1. That's what we just showed. And again, why? It's because when you FOIL this out, you have an x to the n that cancels with my f of x. And I have this term here that has a single power of h. And every other term, just by this thing of adding 1 to the power of h, all these terms have powers of h. Right?
So is the,
Yeah.
sorry, so is the derivative just bringing down the power and then subtracting it by 1?
Well,
Or subtracting it by, yeah,
sorry. For power functions, that is the fact.
okay,
That's what we just proved, right?
yeah.
When the function is x to the n, the derivative is n x to the n minus 1. And this is called the power rule. That's what we just showed. So yeah, so now what we can do is, remember when we had our x to the 4th, we could do it the long way, but we just found out a quicker way, but we proved a quicker way. So you tell me what it is.
Be 4 to the 3rd or x to the 3rd.
And again, this is the reason why it comes from a limit. We just proved a formula, right? So this is not the derivative, right? It's the derivative for power functions. So it's not the easier way, it's a shortcut. It's using a formula, right? Going from here to here, there's a lot of steps here, right? That's what we did up above here. So we have to show why it's true first before we can just say it. Can't just assume things are true. Okay, so that's the power rule. So, so the end of last class, we mentioned the sum rule. So, the sum of two functions, all it is just you add the y values of each function. So when we think about derivatives, what would the derivative be? Well, let's figure out how to solve that. Take the limit as h goes to 0 of f plus g of x plus h. I'm just plugging in x plus h minus f plus g of x over h. The sum of functions is defined this way, where you add just the y values of each. So I have, the y values of x plus h, the y values of g of x plus h, and the y values of f of x, and the y values of g of x. So from here, can someone remind me what we did at the end of class? How could we how could we arrange this thing into derivatives?
We can break it apart.
Yeah, so let's bring the f's together and the h's together, or and the g's together. So let's bring the f's together. And let's bring the g's together. So notice if I split up the fraction and just use some limit laws, what is this? And what is this? What's the first thing here? What is this? What do we call that? It's the derivative, right? We call this the derivative of g. So that's very nice. So if I see a sum of functions, and when I want to find the derivative, all I do is take the derivative of each term. So why is this needed? It's because, well, if I'm looking at a graph and in terms of tangent lines, graphing a sum of functions is it's not so easy to do, right? So this is not obvious to us. This is not given to us based on what we know about graphing, right? Graphing a sum is not as easy as graphing just a single function. So there's nothing for us to say that the slopes are actually additive, right? I take the slope of this and then I add to the slope of that. Just it's kind of it's not really something that should be very intuitive, but using the limits, then we can say that it's actually it's very easy. You just take the sum of each. So given that, now we can find derivatives of all polynomials. So if I have x to the third plus x squared plus x plus 1, what is the derivative? So now we just showed that when I have a sum of things, I can take the derivative of each term. And we just show with powers, it's with power functions, it's just the derivative of we have that nice formula, right? So I have 3x squared plus 2x plus 1. This one's just based on, these are just based on what you know about lines, and plus 0. Yeah, so it's just 3x squared plus 2x plus 1. So I guess one thing we would want to say is it's kind of obvious to the limit, but what is the derivative of a number times a function? You actually might write it like this. If I have a number times a function. So, for example, if it's like, what's the derivative of 2x squared? Or a number times a function. So just to show that proof, it's very not complicated. You can tell me what you need to do. What can you do? I have cf of x plus h minus cf of x. C is a number, constant, over h. What can you do in that limit?
You can factor it out.
Exactly. Then what's left? What happens when you factor?
You're left with the derivative, like,
Exactly, yeah. So this is very nice. This essentially means you can ignore constants. So if my function is 2x squared, and the derivative is 2 times whatever the derivative of x squared is. And what's the derivative of x squared? C is just a number, C for constant. So I have a 2, and then I have x squared. Yeah, so the derivative of x squared is 2x. So this makes 4x. So 3 sine of x. So I just take the constant out, and then I look at the derivative of sine of x, which is what? So we did earlier.
Cosine.
Cosine. Yeah. All right. So that makes sense. So a few minutes left. Let's just kind of boil down what we did today. We found that the derivative, yeah, I'll be posting a recording. So we had that we did the power rule, that if my function is some power of x, the derivative is the power times x to the power minus 1. And just kind of very obviously, this is only true for not equal to 0, because then it's a constant function, of course. We had the sum rule. We had f plus g, the derivative of a sum. It's just, you take the derivative of each term. We had trig. We had if our function is sine, that the derivative is cosine. And we might not have enough time, but I'll let you look at our, even from what we did last time. Let's say your function is cosine. I'll task you to find the derivative. Don't just look it up. Do the limit. Yeah, it should be negative sine. But you should know why it is negative sine. It's something you should memorize, but for later. But for when we're working with our limits, the reason why it's negative sine is because of this fact. Just really want to kind of hammer that in, is that, right? This all comes from somewhere, right? These formulas, right? So it's one thing just to memorize these things, but if you don't know where they come from, they're pretty meaningless, right? And again, it comes from something very physical, right? This is, again, this is average rate of change. And this is the slope of the secant line. So if you focus too much on kind of memorizing kind of what the derivatives are, then you kind of lose the intuition, which is very important for when we actually solve word problems. What a derivative is be important to understand what we define the derivative of, and stuff like that. But
I have a question.
oh yeah.
Why is that the slope of the secant and not the tangent?
So yeah, when you do the limit, and then it's the tangent. The limit of slopes of secant lines is slope of tangent. Yeah, so it's, the derivative is the limit. But the thing you're limiting is secant lines and average rate of changes.
Oh, okay. Got it.
All right, so I'm gonna stop recording.